Good morning, all of you. I once again welcome you on the third day of the GAN course on fascinating features of n-dimensional smart materials. Today, although we have scheduled the first lecture by Professor Samir Sapra from IT Delhi, although he is on his way due to some of his meeting, he could not leave for Aligarh early. But right now, he is already very close to Aligarh, and by the time I'll finish off this lecture, this tutorial, he'll be here, and then he'll take you to the world of optoelectronics, what are optoelectronic devices, how they work, and how we can improve the efficiency of optoelectronic devices. And I'm sure you must be aware of what are optoelectronic devices, which are basically used in display technology or even light emitting diode, the LED bulbs which we are using these days, the laser lights, the optoelectronic devices basically controls light, detect light, and they are also used in fiber optics, fiber optic cables which we are using for internet and communication. So, although I have this tutorial in the afternoon, so I have shifted it, rescheduled it to the morning session, and now I'll be speaking on galvanostatic charge discharge as well as on electrochemical impedance spectroscopy. But before moving on to galvanostatic charge discharge, can I use that mic also? Let me first ask you a question. What are the devices which we generally use for energy storage? How many devices do you know? There are basically two devices. Both are shown on this screen also. The batteries and supercapacitors or even the capacitors. Do you have any idea what is the difference between a battery and a capacitor? Anyone? From the back, I think I have sometimes discussed in the classroom. Can you suggest where these batteries are used and where do we use these supercapacitors? Do you have any example for supercapacitors? Although you all are using, you all have come by bike. All these bikes have electric start. And for electric start, we do not use batteries, we use supercapacitors. Because when we switch the button, it requires a surge of charge, very high amount of charge to start the reaction so that your bike or scooty or whatever it starts moving. In amount of charge at that particular period of time, and therefore instead of battery we use supercapacitor. So this is the difference on the basis of the applications, that a supercapacitor provides a surge of charge while battery provides, although charge is not very high, but it provides gradual charge for right high amount of charge for a very short duration of. This is only the difference on the basis of their application. There's also, there must be some difference based on their mechanism of working. Do you have any idea about the mechanistic difference between a supercapacitor and a battery? Why they are different? Why would a supercapacitor gives you a surge of charge while battery provides a gradual power for a long period of time? This is because a supercapacitor stores energy in the form of electrical energy directly. It is already stored in the form of electrical energy. The moment you need it, it provides you that charge. While in case of battery, the energy is not stored in the form of electrical energy, but rather it is stored in the form of a chemical energy. Whenever you need that energy, a chemical reaction has to occur, and that chemical energy is then converted to electrical energy. Therefore, battery provides slow power, although for a long period of time. And this is the main difference between a battery and a supercapacitor, my dear friends. Then there is another term called as inductor. Inductor stores energy in the form of magnetic field. They all stores energy, but the mode of storage of energy is different. One uses the magnetic energy or the magnetic field, the other uses an electric field, while the third one stores energy in the form of a chemicals. When they react, oxidation and reduction of the species takes place. Electrons are being released from one side, they are being taken up from the other side, and in this way The electrons flows through an external circuit and we get the required power. You must have been aware about a battery which contains two terminal, anode and cathode. Chemicals are also there. One of the supercapacitors or the capacitors only contains two electrons kept at a very short distance, and between them an insulating material is placed. Just take two materials, two electrodes, two materials, between them some sort of non-conducting or insulating material, wrap them up. This is the photo of a capacitor which we have in our and various other devices. They stores energy, and these two terminals shown over here, and these two terminals are basically connected to two electrodes, and in between them there is an insulating material so as to avoid the short circuit between the two electrodes. And this is a common battery which we use at home, which we also use in automobiles, which we use in our inverters. What is the name of that battery which we use in inverters? I'm not talking of the name of the company, Inva, tubular, and all those things. What is the name, the chemical name of the battery? Lithium-ion batteries we use in mobile phones, electric. Lead acid batteries are the name of those batteries which we are used at our homes. Lead batteries, or the correct name is lead acid batteries. Have you ever bothered about the material which are being present in those electrodes? What they are made of? Anything, any idea? These lead acid electrodes which we are, these lead acid batteries which we are using in our homes, they contains two electrodes. One is the lead electrode, the other is lead oxide. One side we have Pb, the other side we have PbO2, and in between them we have a 4 sulfuric acid as the electrolyte, and therefore we call this as lead acid because we have lead as electrode and acid as electrolyte. Now, during the reaction, discharging reaction, when we are taking power from the battery, the lead electrode, the Pb electrode, reacts with H2SO4 forming PbSO4. And since when it was in pure form of Pb, it is having zero charge, and now it is forming PbSO4, means Pb is changing from Pb 0 to Pb plus 2. It is undergoing oxidation, and the electrons which are released, they are taken up by PbO2. Now PbO2 is again converting back to PbSO4, and in PbO2, lead oxide, the oxidation state of lead is plus 4. But when it forms lead sulfate, the oxidation state is plus 2. So when Pb forms PbSO4, it is an oxidation reaction. But when PbO2 forms PbSO4, it is a reduction reaction. So in this way, oxidation and reduction are taking place. We have oxidation of lead to PbSO4 one side, and oxidation of PbO2 to PbSO4 on the other, reduction of PbO2 to PbSO4 on the other side. In this way, electrons flow through the system, through the external circuit, and we get required amount of power. At the time when we are not using the battery, when we are charging it, the reactions are reverse. Means PbSO4 from plus 2 state undergo oxidation to form PbO2. From PbSO4 plus 2 state, it is going to PbO2 plus 4 state, oxidation state during the charging reaction. And during the same charging reaction, the PbSO4 one side forming Pb only. So this is the reduction reaction. So in this way, the reactions are totally reverted when we are charging as compared to when we are taking power out of the battery. This is the basic difference, and you must know the purpose of education, of course, is to educate you, is to impart education in you, and for you it is your duty to imbibe the skills, imbibes the knowledge. But The purpose of education is to make you ponder around the things, which we generally do not. Just ponder about around the things, what it is actually happening, what is the concept behind anything. Why didn't you ever thought of that battery which you are using all the time at your home? What is happening? What are the reactions going on? What kind of electrode is being used over there? बड़े online वालों के लिए. So I was saying that the purpose of education is to make you ponder around yourself, how anything is being done, what are the principles, what are the mechanism behind a particular thing which is happening. Especially being a science student, you should think of it. Now, almost all batteries and capacitors, and the difference between a capacitor and supercapacitors is only very minor difference, is that it is only in the terms of power. The power output for a supercapacitor is very high, therefore it is called a supercapacitor, something which is of superlative degree. Construction is same, everything is same, only the power output is very high for a supercapacitor, therefore it is called a supercapacitor. Okay, there were some issues with the online participants, so they were not able to hear. So I am just repeating. As I was saying from the start, the two energy storage devices are the batteries and the supercapacitors. With the major difference in terms of application is that a supercapacitors provide surge of charge, surge of power at at one point. Means it provides very quick, it gives very quick delivery of power, while a battery provides gradual power, although for a long duration of time. The difference, this difference is because of their mechanism. On one side, we have a capacitor which works electrostatically because it stores charge in, or it stores energy in the form of electrical energy. On the other hand, a battery does not store energy in the form of electrical energy, it stores energy in the form of chemical reaction. Whenever we need power, reactions starts taking place, resulting into the oxidation, reduction of the species, electrons are released, they flow through the outer circuit or external circuit, and we get power. Since chemical energy has to be created, that then it is converted into electrical energy, therefore it takes some time, and battery provide slow power, gradual power. Then I told you that there is one more such device which is called as inductor, that stores charge or energy in the form of magnetic field. So these are the three systems. We very frequently use batteries and supercapacitors. You all are using in your electric vehicles for electric start. The electric start, we always require high power to start the engine. Therefore, instead of batteries, we use supercapacitors for the electric start only. While for rest of the application, like the flashlight, yeah, indicator light, it is with the help of battery, and they all provide DC power. I'm sure you must be aware of that battery supercapacitor, they all provide DC power, and the power which we are getting in these lines, this is an alternating current. Do you know the purpose of the charger? The purpose of charger is just to convert an AC to DC, because our devices are direct charge DC devices, while the power is AC, so they just convert in AC into DC so that our devices can be charged up. Now, a battery, the main components of a battery are anode, cathode, and the electrolyte. Anode is the electrode which always undergoes oxidation, especially when we are using power. Whenever I talk of batteries, it means I'm talking of the discharging process, the process which we are using when we are drawing power from the battery. So always anode undergoes oxidation, releasing electrons, producing cations. On the other side, we have then these cations move towards the other electrode through the electrolyte, and in this way, it is the electric current is being generated. A figure is shown here, where you can see the two electrodes, the positive electrode is surrounded by anions, while we have negative electrode surrounded by cations. They move through these electrolyte system. The ions move through electrolyte while the electrons move through the external circuit, and in this way current is being generated. These are the various devices nowadays where we are using batteries. All these devices we are using batteries. Even your lithium ion battery is also used here in mobile phones, in camera. Lithium ion battery which is being used nowadays has very high uh, it can provide stable power. It can be used for a long period of time. It has very good charging capacities, charging discharging capacity. You can use it for years. The only issue with the lithium ion battery is the overheating and the energy density. The main thing is overheating. It heats up during the process, and there has to be some method which should be devised to control its excessive heat, to absorb its heat so that the temperature should be kept normal. Now, what are capacitors? As I told you in the beginning, a charger is a simple, capacitor is a simple device which consists of two electrodes, of course, a positive and a negative electrode, which are kept aloof from each other by placing a non-conducting or an insulating material in between them, which is also called as a separator. For example, you can see here they have taken two electrodes. This is the anode and this is cathode foil, and in between them they have placed the separator. Just take two electrodes. For example, we have this electrode one side, another electrode. Just put the separator in between them and just roll it. It forms a it forms a capacitor. If the power is very high, it is called as supercapacitor. That's it. They have connected two terminals to it. They wrapped it, and now the terminals are outside this whole assembly, and this is nothing but your capacitors. You can make it very easily. It is used as I said, it provides a quick burst of energy, a surge of charge. So it is used in camera flashes also, power regulation, signal processing, and electronic circuits also, and your electric start in your bikes. Now let us. The supercapacitors are also of two types. Broadly, these supercapacitors are either called as EDLC supercapacitors or pseudo capacitors. Now, what is the difference between an EDLC and a pseudo capacitor? EDLC's the full form is electrical double layer capacitance. And electrical double layer capacitance means it is actually storing energy in the form of a double layer. How that double layer is formed? We have an electrode, for example, it is positively charged, all negative ions will be absorbed on it. Then on the other side, we have a negative electrode, all positive charge will be absorbed over there. So in this way, when we fully charge the supercapacitor, all the negative ions will be at the positive electrode, all the positive ions will be at the negative electrode when it is fully charged. The moment we start using it, the moment we start drawing power out of the capacitor, these ions, which are already absorbed on their opposite electrodes, they start moving, and this motion continue as long as the charge becomes neutral, it becomes equal on both the electrodes. For example, when we have charged the battery supercapacitor, one electrode is having a higher charge, the other is having lower charge. When we start using it, we are withdrawing power, the charges are coming closer to each other, and the moment they becomes equal, our mobile phone shows that it is discharged. Again, we have to plug in. When we plug in, again external energy is provided so that all the charges are deposited on the opposite electrode, and again there will be a gap. One is positively charged, other is negatively charged, and once it is done, all the ions are at the opposite electrode. It shows that it is 100% charged. Now, pseudo capacitors. I'm sure you are all aware of the word pseudo means They are not a perfect capacitor. Why? Just like in chemistry, we call the pseudo first order reaction because the reaction is first order, but it looks like a second order on the basis of number of reactants. You may have two or three reactants. You thought initially that since two or three reactants are participating, it is a second order or third order reaction, but some of the reactant may be in excess, and the reactants which are in excess does not have a role on the rate of reaction. So actually the reaction is first order, it looks like a second order. Such kind of reaction we call as pseudo first order reaction. Similarly, pseudo capacitor means the word quasi or pseudo, whenever they are connected, that means the phenomena is not 100%. There must be some mixing in the phenomena. Similarly, pseudocapacitors stores charge like a battery. Therefore, it is written over here, the double layer capacitors or EDLC, they stored charge electrostatically. Means electrodes have opposite ions over them in the charged state, and when we start using it, the ions moving towards the other side, and when the charge of both the electrodes becomes equal, it shows that now ions cannot move because charge on both sides is same, it is discharged and it needs immediate charging. On the other side, pseudo capacitors are those which are capacitor but they behaves like a battery. They store charge electrochemically. Electrochemically means an electrochemical reaction has to occur, then only charge will be created and electrons can flow from the circuit. So if we use activated carbon, 2D carbon, graphene, carbon nanotubes, carbon aerogels, they mainly use for electrochemical double layer capacitance because they have good conductivity and they have very high surface area. For high surface area, electrodes are preferred for EDLC type of supercapacitors. On the other hand, if we are using polymers, because polymers or various metal sulfides, metal nanoparticles, they are very reactive. They react, they undergo oxidation. Polymers may undergo oxidation or reduction. Metal ions undergo oxidation. So, since they are very reactive, these, when used as an electrode, they prefer to behave more like an electrochemical system. And therefore, such a capacitor where these type of chemicals, these type of materials are used, it behaves as a pseudo capacitor because it is a capacitor but its mechanism is more of a battery. It provides some power, high power, but its mechanism is more of a battery. Therefore, it is not a correct capacitor. It is called as a pseudo capacitor, not actually behaving the way a capacitor should behave. If it is behaving the same way, it must store charge electrostatically. And if it stores charge electrostatically, it is called as EDLC. And then there is third category, hybrid capacitors, because even we are also working on developing supercapacitors and we are also testing different materials. We have developed graphene, carbon nanotubes also, which as I just mentioned that behaves more like an EDLC, and we are also working on metal nanoparticles or metal oxide nanoparticles. They work more of a pseudocapacitors, and sometimes we make a composite of these carbon nanomaterials and metal oxides. So since we are taking two different materials with two types of properties, we got a synergistic effect, and because of that synergistic effect, instead of full EDLC or full pseudocapacitive behavior, we got a hybrid behavior. Means when we draw the curves of cyclic voltammetry or LSV, it shows the occurrence of both the phenomena, which means that some of the ions are being stored electrostatically while some other are stored electrochemically. Clear? This is, as I just mentioned, that in case of an EDLC, electrochemical double layer capacitance, we have two electrodes. For example, we have with this side we have positive electrodes, so all the ions will come on this side. On the other side, we have the opposite ions, and in this way, two layers, charge layers, can be seen on either side. Can you see it? This is nothing but called a double layer. We have double layers. Therefore, they are called as electrochemical double layer capacitors. And it is the charged state. This state where all the ions are absorbed on the opposite electrode No ion is in the between. This shows that 100% charge state. The capacitor has not been used. The moment you start using it, these negative ions will move towards that side while positive moves towards this side, and at a point will come when the charge of the two electrodes remains same, becomes same. The moment it happens, the the capacitor will be discharged. It will ask you to recharge again. The power backup system, electric vehicles, consumer electronics devices may we prefer EDLCs. Wherever we need surge of power. In your electric vehicles, we have to use EDLC. If we are using pseudo capacitors or a battery, it won't work. When you start, when you want to start, it will start after 10 minutes because it has to, some chemical reaction has to occur. Therefore, it cannot be started immediately. Now, pseudo capacitors have chemicals stored in them. For example, metal or metal ions, if they are stored, they undergo a reaction. For example, metal undergoes oxidation, they release electrons. Those electrons are taken up by the electrode. Because I told you, I think on day one, that the difference between a chemical and electrochemical reaction is that in case of an electrochemical reaction, electrons are taken up not by other chemicals directly. Finally, electrons are taken up by the acceptors, but in between them there is an electrode. When the oxidation takes place, electrons are released, they are taken up by the electrode. They travel from the electrode to the other side through external circuit, and from then at the other side they are accepted by terminal electron acceptors. So in between them, electrodes play their role, and therefore they are called as electrochemical reactions. So in case of pseudo capacitors, when metal ions, they release charge, the metal releases charge, they form ions. This electron are immediately taken up by the electrode, they are transferred through the external circuit, and when the electrons reaches to the other side, they are taken up by some other metal ions to reduce. That metal ion will undergo reduction. On one side we have metal ion which undergo oxidation. So this type of behavior will be observed in case of pseudo capacitors. And the material used, as I said earlier, metal oxides are preferred. Even directly you can use metals, metal salts, metal oxides. You can also use conducting polymers. And these type of supercapacitors are used in hybrid vehicles which works both on petrol and batteries, industrial power management, and energy storage applications, high end energy storage applications. This is the model of a hybrid supercapacitors. Do you know the difference between a Faradaic and a non-Faradaic process? Okay. Faradaic processes are those processes where electricity is generated by a Faradaic reaction. Faradaic reaction means when electricity is generated by a redox process, it is called a Faradaic process. And when energy is not generated by a redox process, it is by some other means. For example, you have given energy from outside, it is called as a non-Faradaic process. So in EDLC, in hybrid supercapacitors, we have both the phenomena, a Faradaic and non-Faradaic. Depending upon the type of material, the conditions, there may be more of Faradaic phenomena as compared to a non-Faradaic phenomena, or on the other hand, we may have more of a non-Faradaic phenomena. It depends upon the nature of the material as well as the conditions. But in case of hybrid supercapacitors, we have both these phenomena occurring at a time. The Faradaic process as well as a non-Faradaic process. So when you are learning or studying electrochemistry, you should know all the terms. What is resistance, what is reactance, what is the difference between a resistance and an impedance, how the resistance of an AC circuit is being calculated, how for a DC we calculate the resistance, which you all know, very simple calculation, but for AC it is a bit tough. I'll be covering these topics in my lecture tomorrow. These are the few energy storage where we are using portable electronics, electric vehicles, grid level energy storage, and renewable energy systems. Now, how to characterize a supercapacitor or a battery? Whenever we design a battery, how do we characterize it? Symmetric and asymmetric capacitors are those if you have the electrodes identical, the two electrodes are identical to each other, they are called as symmetric supercapacitors. while if the electrodes are non-identical, they are called as asymmetric supercapacitors. You can also classify a supercapacitor on the basis of their type of electrode into these two categories, symmetric and asymmetric. On the basis of mechanism, you can divide it into three categories: EDLC, pseudo, and hybrid supercapacitors. So if you are taking both the electrodes similar, it is a symmetric supercapacitor. Otherwise, if you are using, for example, carbon electrode, for example, if I talk of lithium ion battery, so we have carbon based electrode on one side, and on the other side we have lithium cobalt oxide, another electrode. So it is a type of a asymmetric supercapacitor because the two electrodes are different, they are not the same. Okay. Now, whenever we design a capacitor or a battery, we develop a supercapacitor or a battery, we have to characterize it. We have to standardize it, that how much power it can store, for how long we can use it, and how many times we can recharge it. Because it depends. Not all the capacitors or battery you can earlier the batteries which we were using in even the cells which we are double A and triple A cell, many of the cells are not rechargeable. While some of the cell, for example, I remember that the Duracell was a company that first introduced rechargeable batteries. There is a separate charger for them. You put the cell in the charger and then plug in the charger, and they started recharging. But still there are certain cells in the market which are non you cannot recharge. So first of all, whenever we design a battery or a supercapacitor, we have to test its properties, that how much energy it can store, what is the power density, what is the energy density, and for how long we can use it. For example, you have developed a capacitor which is having very high power. For example, it can store high power density, it can provide high power density, but just after 2 or 3 times recharging it, now it is not able to store the energy. Then what is the point of having that supercapacitor? Because after every 2 3 cycles you have to replace the battery. What about your mobile phone? We charge it 2 or 3 times a day. If we are not traveling, we are at home, we generally charge at least 1 times a day, and we carry a mobile phone at least 2 years or 3 years or even 4 years. So if you do some just rough calculation, we recharge a mobile phone battery at least 1000 times. If we are charging it 2 times or 3 times a year, and we are having that same mobile phone for a year or two, we are at least charging it 1000 times or 2000 times. So we have to test whether the battery remains capable of holding same amount of charge uh, after 1 year that it is holding on the first day, or there has been some deterioration in properties, and whether that deterioration is significant or not. Yes, I agree, all the batteries deteriorates with time, but that deterioration should not be very significant. After 1 year or 1.5 year, it may lose some power, but it should not lose more than 10%. For example, if when it was a fresh battery, it was able to be used without recharging for 24 hours, then at least after a year it should be able to be used for 18 to 20 hours. 2 to 4 hours it's fine, but if in just a 6 months or period of 6 months or a year, if it can only be charged for it can only be used for 4 hours, then what is the point of that battery? You will never buy that phone, isn't it? So whenever we develop a battery or supercapacitor, we have to test certain parameters, and on the basis of those parameters, we decide whether it can be used or not. This is one of the most important parameter, which is called as galvanostatic charge discharge curve. This curve help you to understand that your battery can be used even after 1000 cycle or 2000 cycle or not. And this machine can perform 1000 or 2000 charge discharge cycle in just a couple of minutes. So you don't have to wait for 1 year to carry out 1000 charging and discharging. This machine will do it just in few minutes. So a charge discharge curve or a GCD curve is a standard method to study the charge holding capacity of a supercapacitor or a battery. With this, we identify whether the battery or a capacitor is able to hold charge for a long duration of time or not. A standard curve is like a triangle. We have this line showing charging cycle, and this is your discharging cycle. And the difference between these top position, for example, in charging, it is, you can see this the point, and there is a difference, and it is written ESR. This is basically the internal resistance. It is called as the resistance, yeah, current drop or power drop. It is due to the internal resistance. If this distance is high, this difference is high, this shows that the materials which you have used in designing those electrodes are having high internal resistances. Internal resistance is an intrinsic property. It depends only on the type of material, not on its size and shape and thickness. So if the internal resistance of those materials is high, there will be more drop over here. So it is a triangular curve. But this perfect triangle will only be obtained for an EDLC supercapacitor. While if your capacitor is not EDLC, it is a pseudo capacitive in nature, or it is type of a battery, then the curve would be like this. Again, we have a drop over here, but the curve would be like this. And if the curve is in between them, some portion linear, then curve, though it is a reflection that the capacitor is a hybrid capacitor. It is neither a perfect EDLC nor an perfect pseudo capacitor. So, what do we do in during the supercapacitor, these GCD test? We take the electrode, of course, the working electrode. As I told you that day, we have working electrode, reference electrode, and counter electrode. We put the clip, and then we give voltage. Then we give current to the system, and we measure voltage with respect to time. We give current to the system, a particular value, 1 ampere per gram or whatever it is, the current density, and we correspondingly measure the voltage, and then we plot voltage with time. So if the curve is linear, this one, the curve is linear, this linear curve shows an ideal capacitive behavior. If in case of your sample you got this straight line, it is an ideal super capacitive behavior of your material. Means the capacitor which you have developed is an EDLC. On the other side, if it is more of a curve, then it is a pseudo capacitive behavior. Then that means your capacitor is not holding it electrostatically, but it is holding the charge electrochemically. And the sudden drop in the voltage, for example, when you have given some current, you started the experiment, there is a rise in the voltage, then there is a sudden drop. This is called as linear drop, but this is called straight line, upside down line. This shows immediately there is a drop. This shows this drop is due to the internal resistance of the circuit. Now, how to analyze a GCD curve? A single GCD curve, when you draw a GCD curve, it first of all gives you the information about an EDLC. Write down what information you are getting from an EDL, from GCD. From a GCD, first of all, the information you retrieve is whether the material is of an ideal capacitive nature, or it is of a pseudo capacitive nature, or of a hybrid nature. First information that you retrieve. Then you can also calculate the specific capacitance of the materials. You can also calculate the power density and the energy density. Now, what is power density? क्या होती है power density? पावर के बारे में सुना है हम लोगों ने, क्योंकि कुछ बीएससी के स्टूडेंट्स भी हैं, दैट्स व्हाई आई एम श्योर जो रिसर्च स्कॉलर्स हैं दे मस्ट बी अवेयर ऑफ, इवन मास्टर्स स्टूडेंट. देखिए पावर डेंसिटी, wherever there is a term density, it means the power or the energy is calculated in terms of unit mass or unit volume. For example, if I tell you that the volt, the power, the potential, yeah, current density of a material is, for example, 1 gram. 1 ampere per gram. That means, for example, we are giving 1 ampere per gram current density. That means we are giving 1 ampere of current for every gram of the material. If we are using 10 gram of the material, then will give 10 amperes. 10 gram, 10 ampere. We divide, the density will be 1 ampere per gram. So whenever the term density comes in, it is either the value divided by volume, or by the area, or by the mass. You can have areal densities, area current density also. You can have volumetric current density also, where we divide the current by volume. And you can have, if only it is written current density, then that means current per unit mass. Similarly, power density means power is shown in watt per gram. Energy density is, what is the unit of energy? How you pay your bills? You pay in terms of unit, that we have this month consume 500 units. Sometimes you consume in summers, because of AC, we consume 1000 unit, even 2000 units. The bills will be high. What is unit? Uh, the unit is kilowatt per hour, or even watt per hour. That can be divided by 1000 to get kilowatt per hour. So watt per hour is the unit of energy basically. Watt is for power, and watt divided by time. Power divided by time gives you energy. And when I say the term energy density, that means power is divided by time as well as the mass. Clear? So it is kilowatt hour per gram also. So from this GCD curve, we can calculate the power density, the energy density, the specific capacitance, as well as the nature of the curve, nature of the material, whether it is electrostatically storing or electrochemically, whether it is having Faradaic phenomena or non-Faradaic phenomena. These are certain, because it's a tutorial class, I'm also telling you the formulas, the specific capacitance, the whenever you do the GCD, start the GCD, I'll show you the screenshots also of the machine. It will ask you what current density you want to carry out these reaction, because whenever we are doing charging, even when we are charging our mobile phones, the phone's battery is taking current from the main line. So basically current is responsible for taking the charge from one side to the other side. So it will ask you at what current density do you want to carry this particular test. So for example, we have selected 1 ampere per gram. It's quite high value, 1 ampere per gram. Then we have to select the few other parameters, and finally it starts giving the data. Once the curve is obtained, from the curve we can obtain the discharge time, the total time from the top point to the, this is the discharge time from here till here, how much time it is taking. Similarly, charge time from here till here, this is the charging time. This blue portion x on x axis, this is the discharge time. So for specific capacitance, the formula is I is equal to C is equal to I into delta T divided by M into delta V. Again, I is the current, delta T is the discharge time. Higher the discharge time, higher will be the specific capacitance, because you see it is in the numerators, delta T. Higher the time of discharge, for example, your mobile phone is discharging after 1 day, that means you have 24 hours, so you have to put 24 here. So specific capacitance of the battery of your mobile phone will be very high. Then we divide it by the mass of the active material. Mass of the active material. Active material pata hai na? I told you yesterday, when we make the electrode, we need 4 materials: solvent, then we add binder, then we add conducting material, acetylene black, and then the active material which we have developed. First of all, dissolve binder in the solvent, put conducting material and active material. So that basically on the basis of that mass of the per unit mass of the active material. The energy density can be calculated from, once you have the specific capacitance value, because we have placed in it order. Order means you have to calculate the specific capacitance first. Once the specific capacitance C is calculated, you can put the value of C 1 upon 2. जैसे होता है ना kinetic energy 1 by 2 mv square. Similarly, we have energy density 1 by 2 multiply by C, the specific capacitance, plus multiply by change in voltage, square of the change in voltage, delta V square. Again the unit is किलोवाट आवर, और वाट आवर में भी लिख सकते हो आप, वैल्यू बढ़ जाएगी, जैसे जूल को किलो जूल में कन्वर्ट करते हैं तो वी डिवाइडेड बाय 1000, तो यू मे रिपोर्ट इट इन वाट आवर पर ग्राम और किलोवाट आवर पर ग्राम. पावर डेंसिटी अगेन watt per gram or kilowatt per gram. IR drop, it is the internal resistance, it must be given in the form of ohms. Just this is this is the IR drop, this gap is the IR drop, this gap is the IR drop. So just from single analysis we are getting so many information, so many parameters we are calculating, and then the cycling stability, because yes, whenever you are doing GCD, it will ask you up to how many cycles do you want this analysis to continue. So you select up to 100 cycle or 500, even 1000. It depends upon the quality of your machine. You cannot do up to 1000 or 5000 cycle for every potentiostat, on every potentiostat. It depends upon the quality of the potentiostat. Otherwise, it heats up and it won't give you reliable data. If you have an electrochemical workstation, you can easily do it up to 5000, even 10,000 cycles. 5000 or 10,000 cycle means it will tell you the performance of your battery even after 1000 or 2000 or 5000 times charging and discharging. What it will, how it reacts even after so many cycles. Will it have the same capacity to hold the charge or not? Then how will you interpret the data? The data interpretation is being done. Again, as I told you, these are the ideal curves. We generally do not get these types of curves. This is an ideal curve which shows an ideal capacitive behavior. Even in our study, for a long time, we never got this result. We always get curved structure which represents a hybrid capacitive behavior having both EDLC and pseudo. Sometimes the linear portion is more, sometimes we have the curved portion is more. If linear portion is more, we can say that it is having more pseudo, more EDLC behavior. Then, so how will you interpret the data? First of all, you have to look at the curves, whether they are straight, they are linear, or they are curved. The second thing is the IR drop. IR drop is basically you have to look for straight line downwards. For example, if I show you this graph, it is linear. Straight up is this, straight down is this. But even this portion is also having negative slope going down. But if you look at this portion, this is small line, here it is going straightly down for a short, well, it's very small portion only, it is going down. This portion is called as IR drop, internal resistance drop. It is due to the internal resistance. If the length of this straight down is high, is long, this shows your material has very high internal resistance. If it is low or if it is not appearing, then that means internal resistance of the material is very low. Now from the GCD curves also we can calculate, as I told you, we can calculate the capacitance, the specific capacitance. So you can plot the specific capacitance. Look in this graph, I think sure it is visible to all of you. In this graph you can see on y-axis we have plotted capacitance retention, means the retention of capacitance after certain number of cycles, and on x-axis we have plotted number of cycles, 1000, 2000, 5000. Even the mobile phone which you are using for the last 2 years, you have not charged it up to 5000 times. In 1 year we have 365 days. If we are charging it twice in a year, we are charging it around 700 times. In 4 years we are charging up to 1500 times only. So we have taken data up to 5000 cycles, which means that we have carried the same battery, the same phone, or the same bike where we are using that up to 10 years. Then only we can achieve this. So even after, you can see this, the red line, these are the two different materials which we have prepared in our lab. They are graphitic carbon nitride. Carbon nanomaterials are of different types. We have graphene, as explained by Professor Hetao, which is only a thin sheet, single layer of graphite called as graphene. Now, making graphene out of graphite is very difficult. The process which we use, the exfoliation method which he has explained, will not produce graphene, but it produces graphene oxide. When we do that process, the single sheet which is obtained, it is a graphene oxide, and it contains various oxygen atoms in its on its surface in the form of OH group or COH group. And because of the presence of oxygen atoms, the conductivity of graphene oxide is much lower. The conductivity of graphene oxide is much lower than graphene. But the problem is we cannot directly obtain graphene. So what do we do is, we take graphite, do exfoliation. After exfoliation, we got a single sheet of graphene oxide, which which contains oxygen atoms and has low conductivity. Then we remove those oxygen atoms by some process. We do reduction, and the graphene thus obtained from graphene oxide, the material thus obtained is not called as graphene, but it is called as reduced graphene oxide. भाई ऐसा भी तो कर सकते हैं कि ग्राफीन ऑक्साइड से शुरू किया, रिड्यूस कर दिया, तो ग्राफीन बोलना चाहिए उसको. Because the process of reduction is not 100%. Not all the oxygen atoms have been reduced. अगर सारे reduce हो जाते, सारे remove हो जाते oxygen atom, then we can easily call it as graphite oxide से, graphene oxide से we have prepared graphene. But कुछ oxygens रह जाते हैं. Because of the presence of very few, we do not call this as graphene, because graphene make भी नहीं होता. We called it as reduced graphene oxide. And its structure is quite similar to graphene. Its conductivity is also improved as compared to graphene oxide, because now majority of oxygen atoms, OH groups, COH groups have been removed. So conductivity has already been improved, but not 100% or not exactly equal to graphene. Graphene still have very high. So similarly we have another material of graphene, which is called as graphitic carbon nitride. Graphitic carbon nitride, C3 and 4. We represent it with C3 and 4. So instead of graphene, we have used graphitic carbon nitride, and we have doped this graphitic carbon nitride with cadmium stannate nanoparticle. So on one side we have metal nanoparticles, and I told you just that metal nanoparticles are very good pseudocapacitors, very good for pseudocapacitive electrodes. On the other hand, I told you that carbon nanoparticles, because of their higher surface area, they are good for EDLC. So since we are using the two, so we got a synergistic effect. The resulting data shows that in our electrodes, because of the presence of these two materials, we have supercapacitive, we have pseudocapacitive as well as EDLC behavior, which means that in our system, the charge was stored electrochemically as well as electrostatically. And when we performed the cycling test to check and evaluate the performance of the battery, even after 5,000 cycles, so you can see the capacitance retention in one of these material, the difference between the two material is nothing. In one of them, both are same, thus the duration of heating is different. They have chemically both are same. So both shows very good supercapacitance and cycling stability even after 5,000 cycle. In case of the graphitic carbon nitride and cadmium stannate, in which it has been calcined at 500 for 2 hours, we have 94% of capacitance retention. For example, if it is being used for 100 minutes earlier, now it can be used for 94 minutes. That too after 5,000 cycle, which is itself very good performance. While in case of the blue one, we got 90% of capacitance retention. Earlier it was 100 minutes, now it is 90 minutes. So we have got these results. These results I am showing just to show how we can interpret a GCD data, how we can interpret the GCD curve. These are the actual GCD curves which we have got for our studies. So if I ask you, so यहाँ पे you can see that a small line going immediately down with very sharp downfall. This shows an IR drop only, while the rest of the portion is not. It is a slope. It is a linear slope, almost linear with a negative slope. But this portion at the top has some IR drop. And these lines you can see if you compare the first curve with the fourth one. In the first curve, we have almost linear behavior because the first curve is of graphitic carbon nitride pure. And graphitic carbon nitride, I just mentioned that carbon nanomaterials, because of their high surface area, they are good for electrostatically storing the charge. Therefore, the curves are almost straight, showing linear curves. But as we start doping metal nanoparticles of cadmium stannate, we are basically introducing something which is more of a pseudo-capacitive nature. And because we are doping it, the curves are getting little bit, the plots are getting little bit curved. Earlier they were quite linear in the first figure, while as we take the B, C and D examples, they are getting more curved, the plots. This shows that higher percentage of cadmium stannate because they are metallic nanoparticles, and metallic nanoparticles are very good for Faradaic reactions for electrochemically storing the charge. So I'm sure those who are working in this particular area, next time when they do the GCD analysis, they can easily retrieve required information from their curves, and they can just when the time at the time when system was plotting it, they can identify the nature of their materials. This is the screenshots. Uh, First of all, the process involves electrode, cleaning the electrode in the shape of 8 alumina water का slurry बनाते हैं, then cleaning in the shape of 8. Electrode is clean, then we go and do weighing of the materials for preparing electrode. Then we take the binder, put it in the solvent. We can use ethanol, methanol, NMP, any solvent depending upon the requirement. Because we have to maintain the viscosity. Very high अगर viscosity होगी तो solvent को लगान, we can paste it easily, but it will not form a uniform coating. And if the viscosity is very low, it will not stick properly. मैंने बताया था कल आपको बताया था yesterday. In the solvent you put binder, then conductive material and active material, make the paste, and there are certain methods. I explained you several methods like screen printed electrode, drop casting, spray coating method I have explained yesterday. We use drop casting method, which is a simple method, but since we are doing it manually, देखो manually आप layer develop कर रहे हो, that layer can be developed, but अगर exactly मैं देखूं तो the thickness will not be very uniform. So for laboratory studies, drop casting is good method, but for large scale, for very reliable data, you have to use certain other methods in which some machine is involved. You will get a uniform coating. For example, either you can use spray coating, coating, the second method I explained yesterday. Spray coating has very good uniformity of the film, and that spray coating method is preferred for large scale studies, for industrial scale also, or you can go for a screen printed electrode, because in both the cases the thickness is uniform, the electrode form is very good, is having identical properties. But for drop casting, because we are doing manually, there may be some difference in the thickness of the electrode. But the drop casting method does not require any machine, so it is very simple and economical process. That's why we are using it. So this is the system. Once the electrode is ready by drop casting or spray casting, we connect it, 3 electrodes, working reference and counter electrodes. We go to the system. This is you can see charge discharge. It is written over there. We perform charge discharge. We select the current density. We also select the number of cycles, and then we start the analysis. देखिए, in the सबसे पहला, the moment you start run, it start giving this shape. This is the charging line. This is the charging line. Then again, this is the discharging. Again, you can see here also the lines are not linear. That means the materials are not perfectly capacitive. They have electrochemical properties like a battery as well. Then comes the electrochemical impedance spectroscopy. Electrochemical impedance spectroscopy is basically used to study the internal resistance of a system. Most of the time, what do we feel that internal resistance of a material is the only resistance which we may encounter, but there may be more resistances. For example, you are doing a test, and this is not a bottle, for example, this is a sample tape for electrochemistry, and we have, this is not an electrolyte, we have placed electrodes, all the three electrodes. Now this system also has certain resistances. This liquid system, this electrolyte has certain resistances. For example, if the concentration of electrolyte is very high, the motion will be difficult. It is also a type of resistance. How a material, ions move inside the solution? Do you have any idea? Solution के अंदर ions कैसे move करते हैं? देखिए, in an electrochemical system, there are three types of motions through which ions can move. First is called as the diffusion. Through diffusion, ions can move from the bulk of the solution towards the electrode, and from electrodes they can move towards the bulk. The first mode of mass transfer. Mass transfer के तीन methods होते हैं. I should stand there. ठीक. The second method is called as convection. Convection is only possible when we are stirring the solution. घर में आप बर्तन में when you heat water for making tea, the lower bottom layer सबसे पहले heats up होती है, it moves up, upper cold layer moves down. तो एक तरह से थोड़ी देर में बबलिंग होने लगती है, मिक्सिंग होने लगती है. तो whenever mixing is there, you are stirring the solution, then ions can move through convection also. And the third and last mode of mass transfer is the migration. Migration occurs when you give potential to a system. जब आप potential दोगे, positive electrode की तरफ negative ions जाएंगे, towards the negative electrodes positive ions will move. ठीक है, पॉजिटिव की तरफ नेगेटिव जाएंगे और जो पॉजिटिव आयंस उसके पास होंगे उससे दूर भागेंगे क्योंकि उन्हें नेगेटिव की तरफ जाना है. तो माइग्रेशन इज द थर्ड एंड लास्ट मोड ऑफ मास ट्रांसफर, एंड इट इज ओनली पॉसिबल व्हेन यू गिव पोटेंशियल टू अ सिस्टम. इफ यू आर नॉट गिविंग पोटेंशियल, migration not possible. If you are not mixing the solution, convection is not possible. So in absence of these two, diffusion always occurs. This is the main mode of mass transfer, which is called as diffusion. So because of these mass transfer also, there are certain resistances. Because of connections, if the connections are not proper, the clip which you have used on the electrode, it has carbon, ohmic resistance, which creates ohmic resistance. So there are many sorts of resistances, which we study with the help of electrochemical impedance spectroscopy. In case of electrochemical impedance spectroscopy, we plot a graph of Z versus Z prime, or sometimes it is called as ZR versus ZI. ZI or Z prime means imaginary resistance, while ZR or Z is called as the real, imaginary impedance, and ZR is called as the real impedance. Now एक नया सर ने टर्म बोल दिया impedance. क्या होता है impedance? मैं तो वैसे कल बताने वाला था आपको. It is also a type of a resistance, but it is a more comprehensive term. Resistance means because when we talk of impedance, resistance is mainly in DC circuits, but for AC circuits we have impedance to show the actual hindrance in the movement of the ions, in the movement of the charge. So impedance consists of resistance and one more parameter called as reactance. Reactance plus resistance combined to form impedance. So impedance, if I am saying the term impedance, it means I have already included resistance in this. But if I am talking of resistance only, that means I am not talking about reactance. So impedance is a comprehensive term. I should come back. दिखाई नहीं दे रहा है. So in electrochemical impedance spectroscopy, we measure the impedance, which is a more comprehensive term which includes resistance as well as reactance, and we plot it by giving different frequency to the system. Frequency, what is frequency? Because in AC circuit it is not, in AC circuit current moves up and down, while DC it does not move up and down, it moves straight चलता है, इसमें साइनोसाइडल वेव की तरह जाता है. And for example 1000 hertz frequency means in 1 second it is going 1000 times up and down, it's going very fast. So we give different frequency signals and we observe the resistance. The standard curve looks like this: a semicircle, and the semicircle not actually starts from here. If it starts from here, then there are no resistance, solution resistance. Jitna semicircle away from the origin start hoga, this shows that the system has some solution resistance. Now, higher the diameter of this circle, higher is the charge transfer resistance. Then there is also a straight line at the end of this semicircle. A standard curve looks like this. And for a capacitor, frequency is inversely proportional to impedance. Therefore, at high impedance, this region shows high frequency. The initial region shows high frequency, while this region shows low frequency. जबकि ये right side में है, यहाँ पर impedance की value ज़्यादा है ना right side में, but frequency is low. On the other side we have low impedance over here, left side में हमेशा low values होती हैं, लेकिन frequency की value high because inversely proportional होता है for this. So diameter of the curve give you information about the charge transfer resistance, while this straight line will show you Warburg or diffusion resistance. That means if this resistance is high, the ions cannot diffuse easily. This means that the ions are encountering some difficulty while diffusing. Or diffusion, it is the main mode of mass transfer. If diffusion is not occurring properly, that means ions are not moving properly, and since they are not moving properly, the power output for such a system should be low. Clear? So from this curve you have detailed information about the resistance. This portion, this line shows the solution resistance, this is the charge transfer resistance, and the straight line curve Warburg resistance or diffusion resistance. For example, in this study for our system, we have started it from 0, and you cannot see here the semicircle, which shows that in our system mainly we were encountering the diffusion resistance. The solution resistance was not very high, we were encountering the diffusion resistance only. And this machine will also produce the actual value of the total resistance, which basically comprise of solution resistance, charge transfer resistance and the Warburg resistance. Total resistance कितना होता है उसको बनाती है, कैलकुलेट करती है, and it represents it in the form of an equivalent circuit. देखो इन्होंने equivalent circuit भी बना के दिया है. ये equivalent circuit means कि अगर ये इलेक्ट्रिक सर्किट में रेजिस्टेंस इतना होता तो कैसे होता. देखो इन्होंने यहाँ पर रेजिस्टेंस भी लगाए हैं, और आपको पता है रेजिस्टेंस डायरेक्ट जुड़ते हैं और पैरेलल में होते हैं, तो कैसे वो सब कैलकुलेशन आप जानते हो. तो इसको रिप्रेजेंट किया है कि अगर ये सोल्यूशन ना होता और ये एक इलेक्ट्रिकल सर्किट होता तो ये कैसा दिखता. तो इसके रेजिस्टेंस, ऑन द बेसिस ऑफ द रेजिस्टेंस ऑफ दिस RCT, वारबर्ग एंड सोल्यूशन, इट क्रिएट्स एन इमेजिनरी इलेक्ट्रिक सर्किट कि आपका सिस्टम इलेक्ट्रिकली सिस्टम की तरह कैसे बिहेव कर सकता है. तो अगर हम इसको इलेक्ट्रिकल सिस्टम में कन्वर्ट करेंगे तो ये कैसा दिखाई देगा. ठीक है. Good morning, sir. I welcome Professor Samir Sapra from IT Delhi. Give a huge round of applause. Sir, I have started my lecture because you are on the way. I am about to finish. So I have been explaining the electrochemical impedance spectroscopy, which is basically used to study the internal resistance of the system, and it gives you information about these four types of resistances: the solution resistance, charge transfer, double layer capacitance, and Warburg resistance. The Warburg is also known as diffusion resistance. Higher the value of resistance, lower will be the power output, lower will be the cycling ability of the material, and then it converts it into a electrical circuit also. Now data interpretation. The high frequency intercept in this curve, on the left side we have high frequency region, on the right side we have low frequency region. It is the ohmic resistance. The diameter of the circle gives you an information about the diameter gives you the information about the charge transfer resistance. The larger the semicircle means, larger the diameter means poor conductivity due to diffusion limitations or maybe some other reasons. Smaller the circle means smaller the diameter shows lower resistance, and your system is has very good electrochemical properties. This is will bring the machine also today to show you in real time mode. This is only the screenshot which we have connected over here for calculating impedance spectroscopy. First of all, after making all the connections, we have to scroll down from the system, select impedance spectroscopy, and after giving some input parameters, it starts making a curve. The curve manages, as I told you, the curve, it starts, for example, it starts from after 100 ohms. So 0 to 100 will give you the ohmic resistance, and from the point at which it forms a semicircle, it gives you the charge transfer resistance, and the straight line at the end, Warburg resistance. So in this way it is being formed. Again, a comparison of the GCD and EIS data. The method, in case of GCD, galvanostatic charge discharge, we have to give a constant current to the system, and we monitor the voltage correspondingly, and we plot the voltage versus time at a constant current density. While in case of EIS, we give small AC signals, small AC frequencies sweeps to check the system's response and to calculate the impedance. So this is the input. We give input constant current for GCD, while we give AC signals over frequency sweeping for EIS. The output for a GCD curve is a potential versus time chronopotentiometry type of curve, while in case of EIS, the output is the impedance versus frequency plot, or impedance versus impedance, the Z versus Z prime plot or Z versus frequency plot. The key parameters which may obtain from GCD are the capacitance, means specific capacitance you can calculate from GCD. You can also calculate the IR drop, the internal resistance drop. You can also calculate the, from specific capacitance you can calculate the power density as well as the energy density. So various parameters can be obtained with these GCD curves. Then from EIS, because EIS is mainly useful for calculating the resistance, so it will gives you an idea about the resistance, and from the resistance you may have an idea about the interface process transport phenomena, how they are working. For example, if you have very high charge transfer resistance, then ions are not being able to move easily in the solution, then there must be some diffusion limitations. So it will give you an idea about the transport phenomena or the mass transfer processes that are occurring in the system. Why we use from GCD, we compare we calculate the cycle life, the cycling ability, we also calculate the energy and power, and EIS is basically used for calculating or determining or diagnosing the system's transport phenomena and the resistances. So last concluding slide, as I have been focusing on GCD and EIS, so both are very useful techniques for those who are working especially in the area of energy storage devices, batteries, supercapacitors, to know the specific capacitance, means the charge holding capacity of the battery or the capacitor, and to know whether they are storing it electrostatically or electrochemically. And we can also able to identify or study the transport phenomena taking place in the system, the values of the energy and power density, the values of the specific capacitance as well as the cycling ability. So with this, I hope you have got some, an idea about the GCD and EIS and how they are useful for characterizing an electrode. Thank you very much. Now